Hi, and welcome to our next session here in our chapter on classification. So, I guess as you can see, I want to introduce the model of logistic regression here in this session. So, our first machine learning algorithm based on the empirical risk minimization principle. I guess we have looked before at k-nearest neighbor as a method, a very simple method to perform regression and classification. Yeah, here we are going to look at logistic regression, and we're going to first of all specify how the linear structure of logistic regression looks like, how we can formally define the hypothesis space of logistic regression. Then we will formally derive its loss function, the so-called log loss or Bernoulli loss that's going to be used in the ERM principle for logistic regression, which is a general and important loss function that's used in many other model classes as well. Talk a little bit about its intuition, why the formula looks like as it does. So we'll algebraically derive it from a maximum likelihood principle, but also discuss its properties. Also discuss linear, or show that logistic regression is indeed a linear classifier based on the concept that we've discussed in the session before. This is going to be fairly simple, and I'll wrap up with a couple of high-level comments on how the logistic regression model is usually being optimized. Okay, so let's start. So our motivation to build logistic regression step by step from scratch, so to speak, is to follow this discriminant approach. So we want to construct a model for binary classification, and we want to specifically construct a probabilistic classifier because we like things being probabilistic. So we'll just choose an encoding. I'll encode classes as 0, 1, and I do want to use ERM because I've said I want to follow this discriminant approach. So the idea is to work with this template structure here. So we have our sum going on over our training data set. So there's n examples in our training data set. They have feature vectors xi. They have labels 0, 1 labels yi. I have my model pi that predicts something on xi based on a parameter vector theta. And then the loss compares the 0, 1 label yi with the prediction pi I and computes some form of an error measurement. And this gives us our empirical risk for one specific parameter vector theta, right? And that was the whole, idea of empirical risk minimization, that this risk function, this empirical risk function R of theta now for every parameter vector assigns some quantitative value to every parameter vector, and we just want to figure out what's the best parameterization for a given training data set, because that's the model we're going to pick, right? So we now turn this learning problem into an optimization problem. But in order for us to concretely do that, we have to become a little bit more concrete for this thing here. So I want to be a little bit lazy to do this step by step. And we want to copy over as many ideas as possible from linear regression. So first of all, we would like our predictive model here to be mainly linear. And what I mean with that, we'll figure out in a few minutes. And I guess that's the two components we have to fix in here, right? At the very least, we have to decide how our model structure pi should look like, our hypothesis space, and we have to also define how our loss function should look like. So let's start with the simplest idea ever. We just steal everything and copy everything over from linear regression. So why not? So we are encoding our labels here as 0, 1. So I guess these are just numbers, right? They are real valued numbers. And if you want to be particularly lazy, we could just say, hey, why not predict these things here with a linear regression model? So nobody ever said that in linear regression, our labels cannot be all 0 or 1, right? So let's just model pi of x as theta transpose times x, linear regression model. And then what loss can we use? Well, everybody uses least squares in linear regression, right? So why not do that as well? As it turns out, you could do that. It's just not very smart. And the problem already starts here with our linear structure for pi of x. So pretty obviously, this model will predict probabilities which can be larger than 1. It could even predict negative probabilities smaller than 0. That doesn't really make that much sense. And even if that does not happen on your training data, it will certainly happen in extrapolation when you use new data points. But there's nothing in the model that restricts its output to at least vaguely resemble something like a probability. And because of that, we usually don't do that. So the first thing we now have to fix is how our hypothesis space should look like to make it more reasonable to really model the structure of these posterior probabilities. So we do want to stick with our linear model structure here. So our theta transpose times x, we like that. The thing is, we'll not really use that to model our posterior probabilities directly. In a certain sense, we'll pretty much very much in a sense, we'll use that to model our score for our positive class. And this score is, in order to turn this into a predicted posterior probability, we'll squash that through a so-called sigmoidal function. Okay, terminology, sigmoidal function. What does that mean? Sigmoidal function means S-shaped function. And you can see that this function here pretty much looks like an S, right? So sigmoidal usually means slightly different definitions, but here what I mean with that is it's a function which is monotonously increasing, and it goes to 0 when the input goes to minus infinity, and it goes to 1 if the input goes to plus infinity. Yeah? So a function like that, pretty much an S. And the idea is if we have very, very, very small negative scores, this is a very, very strong indication against the positive class or for the positive one. So here we have a nearly 0 probability for the class being positive. And here with very, very large scores, this would be a very strong, and we would have a very strong confidence in the class being positive. And for logistic regression, we'll use a very specific sigmoidal function, which is the so-called logistic function. And I've written down the formula here. So, well, I guess I can write down an even shorter version. So this would be x of some score f, some real valued number f, divided by 1 plus x of f. And an even shorter version of this is 1 divided by 1 plus x of minus f. Yeah? So divide that thing here by x of f in the numerator and denominator, and you'll immediately get to this form here. There are other options. You can basically use any kind of CDF, because a CDF usually has this sigmoidal form here, but for logistic regression, we'll specifically use this function here, so this logistic function. And yeah, I'll discuss this now discuss this way more in detail now in the remaining slides of this session. So when we have done that, when we do that, this fixes now our hypothesis space nicely. So we'll use a linear part here to predict our score. And then this is the parameterized part. So theta transpose times x with our theta vector here acting linearly on the features. But in order to predict probabilities, this is now going to be transformed by this S logistic function. A few comments on the logistic. So you can, for example, I don't know, visualize this a little bit. and ask ourselves what happens if we add in an intercept here to our argument. It should be very clear that this intercept pretty much shifts our function horizontally from the left to the right. And if we multiply our argument with some positive constant alpha, this would control the slope. So we can make the slope stronger or weaker, and we can also control the direction. So we can flip the whole function horizontally by using a negative alpha. There's also the inverse of the logistic function. That is usually called the Logit. So you can also easily write down how this inverse function would look like. So this is log of pi divided by 1 minus pi. And some people also call that the log odds, because the odds are pi divided by 1 minus pi. So that's the probability for the positive class divided by the counter probability. Okay, positive logits, they indicate probabilities larger than 50%. So let's maybe go through an example here. So maybe your posterior probability is 75% for an event belonging to the positive class. That would be odds of 3 to 1. Yeah? And the logit here would be approximately, so that would be the log of 3, which is approximately 1.1. So maybe we can also take a look at how the function looks like visually. I guess you can see here that this is pretty obviously the inverse of this S-shaped function we looked at before. And our sigmoidal function took our real line and mapped that to the interval 0, 1. Maybe actually I should probably actually say, I don't know, it doesn't really map to the closed interval and kind of just maps to the open one, right? And yeah, this is now the inverse where we map a probability here to this input value, and this input value was our score. But for the score we now have a nice interpretation, right? Because this score basically tells us how the log odds behave. So maybe you don't like thinking in log odds, but if you then take the exp of that thing, that would allow you to reason about odds. It also tells you, this way of looking at things also tells you that your feature vector x now acts linearly on the logits, controlled by our coefficients theta. So if you do S inverse, so the logit on pi of x, that's log of the odds, but that's exactly the same by construction as theta transpose times x, okay? And if you don't like thinking in log odds, which is difficult for most people, then, and if you want to understand effects of features better, just take the exponential on both sides, and then you can kind of reason in odds. And what you will, this is not really a basic course here on GLMs and their statistical interpretation, but you can then reason about the multiplicative effect of a coefficient on the odds if you look at exp of the coefficient. Okay, so we have now a potential hypothesis space available to us. So we have this pi of x modeled as S of theta transpose times x. So this is how our predictive model should look like for binary classification based on this linear structure and this logistic transfer function. What we haven't really talked about is what loss function we are using here. And what I want to do is I want to derive where this common loss, which is called the log loss, how we can actually derive the formula of that thing from a maximum likelihood principle. So if you have paid attention here, so maybe you are thinking I'm deviating a little bit from what I've said in the beginning. I've said in the beginning, we want to be lazy. We want to copy over as many concepts from linear regression after we have now fixed our hypothesis space and our model structure like that, we could just do least squares on that, right? And I'll talk about that at the end of the session here, where that's not, we could actually do that, but it's usually not commonly done, and there are reasons against that. So what we are doing instead is we are using something that's called a Bernoulli loss, or the log loss, or the coarse entropy, and it has a certain formula, but maybe you haven't really seen where this formula comes from and how this is derived. And I want to do that exactly here now on the next 2 slides, and to make this very clear to you, because it's not that hard to understand where this actually comes from. So what we want to do is we want to start with a maximum likelihood principle. So we're going to look at the likelihood of our model based on our parameter vector theta, and that likelihood simply now multiplies up terms across the whole training data set, where we multiply up pi of xi for positive examples. So if it's positive example, we use pi of xi, so the probability for that class being positive. And if it's a negative example, so if the label is 0, we actually multiply up the counter probability, so the probability of the class being negative, in our likelihood function. So for each observation xi, yi, only one of these 2 cases here is true. If it's positive, we take pi. If it's negative, we take 1 minus pi. And we multiply all of these things up in a large product. Now, this is a little bit, I don't know, not as compact in terms of writing as we like it to be. So we now do a very clever trick to unify these 2, I don't know, factors, these 2 components here. So the positive and the negative ones. The first part with the positive labels, I should probably say, and the second part with the negative labels. And we do that by smartly using exponents here. So we write down a product which now goes over the complete data set. I goes from 1 to n. And here we write down our probability pi. And here we write down the counter probability 1 minus pi. And the first guy we now take to the label y. And the second guy we take to the label 1 minus I. Remember again that the labels, they are encoded as 0, 1, right? So what happens now for positive examples? So if we have a positive example, the label will be 1. 1 minus y is going to be 0. So this here will be 1, and this will not be active, so to speak, in the computation of this product here. And for the first term, y is 1, so this is just pi, right? So we have exactly this thing here from our first product. And if you now set y to 0, because you're looking at a negative case, a negative label, then exactly the opposite happens. So y is 0, this here will become 1, it will not change the value of our product. And 1 minus y will be 1, so this is just 1 minus pi, so the counter probability, so this thing here, so for a negative label. So these 2 formulations are exactly equivalent, and the second one is a little bit nicer to work with. So we'll now use the kind of standard approach, and we'll discuss this way more in detail and see this very, very often again by turning this maximum likelihood principle now into a loss minimization or empirical risk minimization thing by simply working on the negative log of things. So we dislike a little bit that we have a product here, much rather turn this into a sum, and we also usually turn these optimization problems from a maximization problem into a minimization problem. So first of all, we now take the log. So we now look at the log likelihood. So our product becomes a sum, and then the log here, for now, I just pushed this inside of the sum. What happens now with this longer term here? So we have our exponents, they move in front of the log, and our product here is simply turned into a sum. Yeah? So we have label times log of pi plus 1 minus y. Yeah? So I don't know, the counter label, the opposite label, times log of the counter probability. And the only thing that's left for us to arrive at our final structure is to now minimize the thing, which we do by multiplying everything with the minus 1. So we turn the maximization problem into minimization problem. So nothing really exciting has happened here in the last line. You just put a minus in front of everything. And now if we look at that, this is a sum over the complete training data set from y to n, where we do some function here for every observation, where we compare the predicted probability with the label. Okay, granted, it's a more complicated function, maybe than, I don't know, expected, but it somehow compares the labels with the predicted probability of our model. So let's just write down that formula here without the sum, without any superscripts. So it's minus y times log of pi minus 1 minus y times log of 1 minus pi. That's the loss function in our empirical risk minimization that we've seen on the slide before. And that formula we will now simply give a name. Some people call this the Bernoulli loss because it's derived from a Bernoulli model, where we like a coin flip, a 0-1 coin flip. And the probability of that 0-1 coin flip is encoded here by pi of x. We flip a coin for each prediction, for each observation. Some people also like to call this the binomial model for the same reasons. Some people call this log loss because I guess the log function appears in its definition, and for reasons I will also explain later in the lecture here. If we take an information theoretic perspective, some people call that the cross entropy loss. So in order for us to understand this a little bit better, I have visualized this here. I've visualized this in terms of pi, and I've now drawn two curves. So one for the positive class, which is this orange curve here, and one where we're in the negative class, and you can see they are pretty symmetrical. So I guess it's enough maybe to discuss one of the two. So you can see that if we have a positive class, and if we predict something that's larger than 50%, so that would be our standard threshold here, right? So everything on the right-hand side here, we would say our hard label prediction would be +1, and here our hard label prediction would be 0. So if we are on the right-hand side of that 50% threshold, our loss is quite small. But if we are on the left-hand side, and this is where the prediction would be wrong, where our predicted label would not match the observed label, the loss goes up quite quickly. So this type of loss penalizes predictions quite harshly, quite heavily, which are confidently wrong, which is a good thing. And as I've said before, or I guess I've said that in the beginning, I want to say it again now. If you look at this derivation that we did here, at no point in the derivation we really made any specific, reference here to how our model pi I actually looks like. So it doesn't really need to be S of something linear. It can be anything. The whole derivation makes sense for any model structure pi of x, which means this loss function here can pretty much be used for any type of binary classification system, and it makes a lot of sense because it's based on this maximum likelihood estimation principle. And this is the reason why this is indeed used for many other model classes beyond logistic regression. It's heavily used in neural networks. It's very often used in boosting, and pretty much there is no right or wrong loss function. So you can use other things, but there are good reasons to at least give this a try because of the maximum likelihood derivation that I just showed. In pretty much any model class that's based on this discriminant principle. That's any probabilistic classifier that predicts a posterior probability and is constructed through empirical risk minimization. Further small visualization of logistic regression here on 2D data. So maybe with some features x1 and x2. Just I constructed this here on some simple toy data set, which is nearly linearly separable, but not exactly. You can also see that the decision boundary is a hyperplane. So in 2D here, a straight line. And this is also easy to prove now, because you can see that we have this linear structure here, theta transpose times x. And then the only thing that is also in there is that this S function, which is an isotonic function, so a monotonically increasing function. So if we take the inverse of that, the linear structure remains, and that was exactly our definition of what a linear classifier is. And it's also very clear that the decision boundary of that thing, and proved that in the session before, will then be a linear structure, a hyperplane in R to the P or in R to the P plus 1. You can also see here how the scores are transformed into probabilities. If we plug them in a univariate fashion here in our S function, and then look at that. This course here is not a course that's, I don't know, particularly detailed in terms of discussing how these models are optimized. I have another lecture on that, optimization for machine learning. But I want to at least make a couple of comments here so you get at least a rough feeling how the logistic regression model would be optimized. So first of all, our log loss function that we derived here is a so-called convex function that has certain nice properties, especially if you put this on top of a linear model. So under very simple regularity conditions, so let me at least say this orally here. So if our design matrix would be full rank, and if our training data would not be linearly separable, then the linear structure together with this convex loss function here would guarantee that our logistic regression model or the underlying ERM optimization problem has a unique solution. Doesn't have an analytical one, so we can't really nicely directly solve that by computing a gradient and setting it to 0 as in the linear model case, but we can numerically optimize that. And because it's a convex problem, it's at least a simpler case than a non-convex one where we would have to potentially worry about local minima and about restarting numerical optimization. And the usual optimization algorithm depends on data size and many other aspects. But a common choice for, I don't know, common scenarios is some second order principle like Newton-Raphson. So based on gradients and based on Hessian matrices. If our training data is unfortunately completely linearly separable, so if it would look like that, don't want to discuss this here in details. I have a deep dive also in the lecture on that. But if the data is completely linearly separable, our optimization problem, the ERM problem, is actually unbounded. So we wouldn't really find a solution. We could always construct a better one, which is a little bit annoying if you work with logistic regression, but there's also a simple way out of that, and that is to put some form of regularization, for example, an L2 penalty, like a ridge penalty on top of the ERM problem, and then we can turn that unbounded problem into a well-behaving, well-defined one. I'm still owing you an answer to why don't we just use that here? So S of f, or actually maybe I should say S of theta transpose times x, so S of a linear model, to guarantee that our predicted output is always between 0 and 1, and then just use least squares on that. That's actually possible, and that's not as stupid as just using a linear model to model a posteriori probabilities, and that has been done in the past, but it's also, one is also able to show that the resulting ERM optimization problem is now not convex anymore in the parameters theta. This is not, I would say, super obvious to see in a second, but it's not impossible to derive this yourself. So actually a very good exercise to write down the M problem of logistic regression with log loss and then compute the gradient, compute the Hessian. Even better, do that with pen and paper, then implement that. That's, I guess, the perfect exercise. You can also try your hands on the AM problem for logistic regression with the logistic transfer function and then least squares, and try to show that this is not convex anymore. Maybe construct something like a counterexample or think a little bit about why this is convex for the log loss case and what doesn't work anymore here in the least squares case. This is a very nice exercise. I really very much recommend to try this out. I'm not going to do this here because the video is probably already very long already. And this is a basic course, and I don't want to talk too much about optimization details. Maybe a final comment before we stop here. What we can also do is we can write down our empirical risk minimization problem, as I've done this before, but instead of writing it in terms of pi, I can directly write it in terms of f, so in terms of our linear score, without, I guess we've done this before, but there was always this like direct squashing going on with the sigmoidal function. You can also write it down like this here, with a loss function that directly acts on the predicted score f, and by using this loss function here. And this loss function is just another way of writing down the log loss or the Bernoulli loss, but now the loss incorporates the S, and we directly apply it to the predicted scores. So before we had like, I don't know, 3 components, so L, S, and I don't know, F, which was theta transposed times x, equals f. And now we just have the L and the F in a more compact form. This is also a very nice exercise to show that these formulations are equivalent. It's actually much easier than what I suggested before. There are even other versions of writing down logistic regression by now not using 0, 1 labels, but +1, -1 labels. So at the end, I guess there's like at least 4 forms. So one where you decide whether you use a pi or an f, and then another degree of freedom where you decide whether you use +1, -1, or 0, +1 as label encodings. And it's a cheat sheet online for the lecture. We can actually look up all of these formulations and the related encodings and the loss functions. And they are all just different variations of the log loss or the Bernoulli loss, either based on scores or probabilities. Okay, that brings us to an end to this long session. See you in the next one. Bye-bye.